Good evening, everyone. I'm Emily Joy C. Ramos, and for question number 1, the compression ratio of an air standard Otto cycle is 9.5 prior to the isentropic compression process. The air is at 100 kilopascal, 35 degrees Celsius, and 600 cubic centimeter. The temperature at the end of the isentropic expansion process is 800 degrees Kelvin. Using specific heat values at room temperature, determine the highest temperature and pressure in the cycle, the amount of heat transferred in kilojoule, the thermal efficiency, and the mean effective pressure. So first, we must know or we must identify what are the different given. So we have the compression ratio, which is 9.5. We have the initial pressure, which is 100 kilopascal. We have the initial temperature, which is 35 degrees Celsius, wherein we're going to convert it into degrees Kelvin. And in converting this, we all know that we will going to add 273.15 to this value, wherein 35 plus 273.15 is equal to 35 plus 273.15 is equals to 308.15 degrees Kelvin. Another given is the volume, initial volume, which is 600 cubic centimeter. So we need to convert this into cubic meter, wherein in 100 centimeter there is 1 meter. So we're going to raise it into 3. Therefore, 600 times 100 is to 3. Here. 6 times 10 raised to negative 4, or 0.0006 cubic meter. Another given is the T4, which is 800 degrees Kelvin. We all know that the Cp of air is 1.005 kilojoule per kilogram degrees Kelvin, while the Cv of air is 0.718 kilojoule per kilogram degrees Kelvin. The R constant, which is 0.287 kilojoule per kilogram degrees Kelvin, and the constant or the K is equals to 1.4. So now for A, so the highest temperature and pressure in the cycle. So we're going to find for T2, for T3, and for P3. So first for T2. So we're going to use this formula, which is T1 V1 over V2 of raised to K minus 1. And we all know that V1 over V2 is equals to RK. Therefore, T1 V1 over V2 or RK is 9.5. K is 1.4 minus 1. Well, the initial temperature is 308.15 kilojoule per kilogram degrees. 308.15 kilojoule. This is in degrees Kelvin only. Times 9.5. 1.4 minus 1. Therefore, T2 is equals to this 308.15 9.5 is to 1.4 minus 1. Here. 758.3184 degrees Kelvin. 0.3184 degrees Kelvin. So here is the one unknown. For another unknown, we're going to solve for P2. So in solving P2, we're going to use this equation. It's equals to P1 V1 over T1, wherein P2 is equals to V1 over V2 times T2 over T1 times P1. So V1 over V2 is RK, which is equals to 9.5. T2 is 758.3184 degrees Kelvin over the temperature 1, which is 308.15 degrees Kelvin, times the P1, which is 100 kilo Pascal. Cancel. Therefore, P2 is equals to 9.5 times 758.3184 over 308.15 degrees Kelvin times 100 kilopascal. Here, it is 2,337.830,537. 3184, 30815, 2,337.830.5 kilo Pascal. Next unknown is for T3. So for T3, we're going to use the formula wherein T3 is equals to T4 V4 over V3 raised to K minus 1. As if you can see, V1 over V2 is equals to V4 over V3 is equals to RK. Therefore, T3 is equals to T4, which is 800 degrees Kelvin, over the RK, which is 9.5 raised to 1.4 minus 1. Therefore, T3 is equals to 800 is 9.5, 1.4 minus 1. Here, 1,968.6995 degrees Kelvin. So next for pressure 3. So we're going to use P3 V3 over T3 is equals to P2 V2 over T2, wherein P3 is equals to T3 over T2 times P2. Therefore, P3 is equals to T3 is 1,968.6995 degrees Kelvin over the T2, which is 758.3184 degrees Kelvin, times the pressure 2, which is 2,337.8305 kilopascal. So let's solve for P3. So 1,968.6995 over 758.3184 times 2,337.8305. Here. This is the answer. 3184 times 2360. 2337.83